Imagine those giant electric machines, the ones keeping, everything running.
Yeah.
Power plants, huge factory motors.
Yeah, massive pieces of kit.
They rely on something you can't even see, their electrical insulation. It's the unsung hero stopping catastrophic failure.
Absolutely.
But how do you know when that critical insulation is starting to give out before it actually fails? That's a question worth millions when you think about downtime costs.
It really is. And standard insulation tests, they'll tell you if a winding's okay to put back in service. It's sort of a simple go or no go.
Right, pass-fail.
But they often don't tell you why the insulation is degrading or, what kind of problem you're actually dealing with. Is it just wet? Is it old? Something else entirely.
And that's exactly where we're focusing today. This deep dive is all about advanced diagnostic testing for AC electric machinery insulation, specifically using direct voltage.
DC testing.
We're pulling from a draft guide from the IEEE, that's the Institute of Electrical and Electronics Engineers. It's a document designed to help you get a much, much richer picture of insulation health.
Right. This guide goes beyond the basic pass-fail stuff you find in, say, the established standards. The mission here is really to show how certain DC testing techniques can unlock diagnostic information.
So getting a true picture.
Exactly. Understanding the insulation's condition, what potential issues might be lurking inside.
Okay, so why should this matter to you, the listener?
Well, because knowing the real state of that insulation isn't just, academic.
Yeah.
It's key to predicting potential failures, planning your maintenance smartly, and just keeping those critical machines running reliably, avoiding those unexpected, really costly shutdowns.
Makes sense. So let's unpack how it all works.
Okay. So at its core, insulation testing for these big AC rotating machines is about assessing the ground wall insulation.
The ground wall.
Yeah.
That's the main barrier.
Yeah, think of it like the primary barrier. It's the high voltage wall separating the copper conductors, carrying all that power from the machine's grounded frame.
Right. And the traditional DC tests, like the ones in IEEE standards for insulation resistance, IR, and polarization index, PI, or maybe DC overvoltage tests.
Those are great for a quick check. Will it handle a basic stress test? Is its resistance high enough? They give you that essential, can I re-energize this answer?
Okay, the basic safety check.
Exactly. But like we said, sometimes you need more than just yes or no. You need to understand the nature of the problem, what's actually happening. That's where you make informed decisions.
And that's where these advanced diagnostic methods from the guide come in.
Precisely. These are the techniques designed to dig deeper, to help you actually diagnose the specific issue.
Okay. So which methods are we talking about?
The guide really focuses on 3 advanced DC tests that give you this extra layer of diagnostic insight. There's the DC ramp test, or DCR.
Yeah, got it.
Then the polarization and depolarization currents test, PDC.
PDC.
And finally, the insulation resistance profile test, or IRP.
DCR, PDC, and IRP. And taken together, what sorts of insulation problems can these tests help you find?
Well, the guide details how they can help pinpoint things like thermal degradation, that's just basic aging from heat, electrical degradation, so damage from voltage stress,
right.
Problems if the insulation wasn't, say, fully cured properly, degradation of the stress control coating.
That may be voltage in the end, windings.
Exactly. Crucial part. Also, moisture, whether it's just sitting on the surface or if it's soaked deeper in, general contamination, dirt, oil, and even internal tape separation, delamination.
Wow, that's quite a list. Covers a lot of potential failure modes. Now, what kind of things can you actually test with these methods, the whole machine, parts?
Both, really. You can test complete windings. That might mean testing a single phase or maybe all 3 phases together. That gives you an overall picture of the machine's insulation health.
Okay. And testing individual components, like, say, a spare coil you have sitting on the shelf.
Absolutely. The guide talks about testing individual winding components. Could be a spare coil, like you said, or maybe a bar you've taken out of an older machine. This gives you a much more focused look at the insulation material itself and, how it behaves.
What's the real advantage of testing just one part versus the whole winding?
Testing individual components, it can give you a clearer baseline of the insulation's intrinsic properties, how specific degradation mechanisms affect it.
Right, like a control sample.
Sort of, yeah. And then you can compare those results to tests on the complete winding, especially if you use a technique called normalization, which we should definitely talk about.
Okay.
And of course, individual parts have much lower capacitance than a whole winding, so the currents you measure are going to be lower.
Makes sense.
The guide also points out something interesting. On individual bars or coils, these DC tests can actually reveal issues in the end winding region and the stress control coating. Those are areas that don't see much AC voltage stress during normal operation, but they are stressed by the DC during the test.
Ah, so you might catch problems there that AC tests wouldn't stress.
Potentially, yes. So whether it's a whole winding or just a single coil, you're applying a DC voltage, and you're mostly looking at the measured current. The guide says this current is the key variable. Can you break down what actually makes up that total current you measure?
Yeah, let's get into that.
Okay, so when you apply that DC voltage, the total current isn't just one thing, it's actually a mix of different components, and they each behave differently over time. First up, you've got the capacitive current.
Right, the initial inrush, like charging up a capacitor.
Exactly like that. It's high magnitude, but it decays super rapidly, usually gone within a second or so.
Okay, then what?
Then comes the absorption current, sometimes called dielectric relaxation current.
And that one sticks around longer.
Yeah, it decays much slower, over seconds, minutes, sometimes even longer, really depends on the material. This current is related to the polarization of the insulation material itself.
Polarization,
Yeah.
like molecules lining up.
Kind of, yeah. How its molecular structure aligns under that electric field. Its characteristics are tied to the material type, its condition, dimensions, temperature.
Got it. And the last part.
Finally, you have the conduction currents.
These sound like the ones you don't want. The leakage.
Well, yeah, they represent the leakage pathways. Conduction current is the sum of surface leakage current flowing over the outside surfaces and volume conduction current flowing through the bulk material itself.
And these just keep flowing.
As long as the voltage is applied, yes. They're continuous, irreversible. Ideally, for healthy, brand new insulation, these conduction currents should be negligible, tiny.
Okay, so fast capacitive, slower material absorption, and the continuous leakage or volume conduction. But the guide also talks about measuring current during depolarization. What's that about?
Ah, yes. This is a really critical distinction, especially for that PDC test we mentioned. After you've applied the DC voltage for a while, that's the polarization phase, you then remove the voltage and short-circuit the test object to ground. And you measure the current flowing out of the winding. That's the depolarization current. It includes the capacitive current, very briefly again, and more importantly, the absorption current as the material relaxes from being polarized.
So the depolarization current is the insulation giving back the energy it stored inside the material itself, but without the continuous leakage current flowing.
Precisely. That's the key takeaway. By measuring the depolarization current, you can effectively isolate that absorption current component, the part that tells you about the material's internal polarization, its relaxation properties.
And you separate it from the continuous conduction currents.
Right, which are often heavily influenced by external things, like surface moisture or contamination. So this ability to separate them is vital for diagnosis. Is the problem on the surface, or is it something deeper within the insulation itself?
That separation sounds incredibly useful. Now, you mentioned normalization earlier. Why is that conversion needed? Why is it important for comparing results?
Oh, normalization is absolutely essential if you want to compare results from different test objects or even different machine designs. Think about it. If you test a single coil, then a full phase, then an entire three-phase winding.
The raw current readings will be totally different just because of the size.
Exactly. It's like measuring water flow through a garden hose versus a fire hose. Even if the water pressure is the same, the volume is different.
Good analogy.
Normalization removes that effect of the test object's geometry, the number of bars or coils, how they're wired up. You do it by dividing the measured current in amperes by the test object's capacitance in farads.
Okay, so you get amperes per farad, AF.
Right, amperes per farad. You're essentially looking at the current response per unit of its capacitive size.
Which lets you directly compare the material's behavior, regardless of whether it's a tiny coil or a giant winding.
That's exactly the power of normalization. The guide has a great figure showing this. Before normalization, the raw current curves for a whole winding and individual phases look completely different, just scaled differently. But after you normalize, the curves become directly comparable, and suddenly you might see an anomaly in one specific phase. Maybe it has higher leakage that was totally hidden before, it just pops out. That kind of comparison across different parts of a machine or between machines, impossible without normalization.
That really drives home why it's so necessary. Okay, now beyond the state of the insulation itself, the guide is really clear. that other factors can significantly mess with these DC test results. You have to consider them when you interpret things.
Oh, absolutely. If you ignore these factors, you could completely misdiagnose the situation. The primary ones are, first, the type of insulation materials used in that specific machine.
Different recipes of epoxy or polyester or whatever respond differently.
Dramatically differently. Epoxy, polyester, older asphaltic systems, they each have unique dielectric properties, unique absorption characteristics, different levels of inherent conductivity. Knowing the material is fundamental. You need to know what a normal test result should even look like for that machine.
Makes sense. And for healthy, new stuff, conduction should be low.
Very, very low, ideally negligible.
What about environmental factors like temperature or humidity?
Huge influences. Temperature significantly affects the insulation's resistivity. The guide suggests correcting measurements to a standard temperature like 40 degrees C if you can, like they outline in IE 43.
Or at least be consistent.
Yes, at the very least. So especially for tests like IRP where you're trending results over time, you absolutely need to perform the tests at a consistent temperature each time.
And moisture. We know that's a classic insulation killer.
It is. Moisture or water absorption dramatically increases the conduction current. It could be simple surface moisture, or it could be absorbed deeper into the bulk material, especially with older, more hygroscopic materials like asphalt or some polyesters.
Right. Stuff that likes to soak up water.
Exactly. The guide notes this causes the current to increase in a nonlinear way with voltage. They even mention something called the electroendosmosis effect.
Electroendosmosis. What's that?
It's where the electric field itself actually causes moisture within the insulation to physically migrate, to move around, which can sometimes lead to different resistance readings depending on whether you're testing with positive or negative DC voltage.
Interesting. Okay, what about surface contamination?
Yeah.
Dirt, oil, conductive dust.
Yeah, that increases the surface leakage current. The guide points out it can make the measured current response kind of erratic. You might see spikes in the results, particularly in IRP tests.
And finally, what if you're dealing with uncured resins or coatings? Maybe on a new machine or after a repair.
Yes, that's definitely a potential issue. Uncured materials can be inherently conductive themselves, or they can be highly susceptible to absorbing moisture.
Which sounds risky for testing.
It is. It poses a significant risk because these materials could break down prematurely if you apply the full test voltage. So the guide strongly recommends doing an initial basic insulation resistance check with a low-energy tester first if you have any suspicion at all about uncured insulation.
Good safety tip. Okay, so we've got the current components, normalization, influencing factors. Let's dive into the first of those three advanced tests. The DC ramp test, or DCR?
Okay, the DCR. The principle is pretty straightforward. You apply a DC voltage, but instead of just stepping it up, you increase it smoothly and linearly over time.
Like a ramp.
Exactly. Typically, the guide suggests a rate of about 1 kilovolt per minute, and as that voltage is ramping up, you continuously measure the current flowing through the insulation.
And you plot that current against the voltage as it rises to get a curve.
Precisely. The resulting curve, current versus voltage, that's the signature. It shows how that specific insulation behaves under increasing electrical stress. Now, remember those current components we talked about?
Yeah, capacitive, absorption, conduction.
Under a ramp voltage, the capacitive current is actually constant because the rate of voltage change, dV/dt, is constant.
Interesting.
And the absorption current tends to follow the voltage pretty linearly. So if you see significant nonlinearity in the total measured current, the curve starts to bend upwards sharply, or it gets wavy, that often points to the conduction currents increasing, or maybe localized defects starting to become active as the voltage gets higher.
Okay.
Yeah.
And what determines how high you ramp the voltage?
Yeah.
At end of test or EOT voltage?
The guide bases the EOT on the machine's rated line-to-line voltage, the VLL. They use factors derived from standard tests, basically converting the AC rating to a DC equivalent, usually multiplying VLO by 1.7.
Right.
And then they apply an additional factor, typically around 85%, based on experience that these ramp tests are more sensitive and applied for longer than, say, a quick withstand test.
So the guide gives you formulas or tables for this?
Yes, exactly. They provide equations for calculating the EOT. And it depends on whether the insulation is considered new, which they define as 0 to 5 years old, using a 1.5 factor relative to that base calculation, or if it's service-aged, so over 5 years old, where they use a 1.25 factor.
Lower factor for older insulation.
Right, and they provide a helpful table with pre-calculated EOT voltages for common machine ratings. And a key point they make: Any winding that shows visible deterioration is considered service-aged for testing. Doesn't matter how old it actually is on paper.
Makes sense. What if things start looking bad during the ramp? Like the current gets erratic, spikes up, or increases suddenly way before you hit that target EOT voltage. Do you just keep going?
No, the guide strongly recommends stopping early in those situations. If you see clear signs that failure might be imminent, like a rapid, sudden jump in current or current spikes, or a significant change in the curve's slope indicating nonlinearity is kicking in way below the target voltage, you can and generally should stop the test.
To prevent causing major damage right there on the test bench.
Exactly. However, they do mention in some specific cases, say on a machine already in service where you suspect failure might happen soon anyway, you might choose to continue the test all the way to breakdown.
Why would you do that?
It could potentially help pinpoint the exact location of the fault and maybe give you an idea of the kind of damage it might cause if it failed while running, but that's a specific decision, not the norm.
Okay, so the shape of that curve is giving you real-time feedback on the insulation's condition under stress and normalization.
Yeah.
Still important for DCR.
Absolutely crucial for comparison. Normalizing the DCR current by the test object's capacitance lets you directly compare curves from different phases of the same winding, or even compare results from different machines or designs.
Like we discussed before.
Right. The guide has a really compelling figure showing this. Before normalization, the raw current curves for a whole winding and its individual phases look very different just because of their size. But once you normalize them, bam, you can clearly see that one specific phase has a much higher current response at higher voltages compared to the others, an anomaly that normalization just makes obvious. In that example, it was linked to higher leakage current in that phase.
Okay, let's dig into interpreting these DCR curves. What specific things can the shape of that curve tell you about the insulation?
Well, the curve signature provides a whole lot of diagnostic clues. First off, just the basic shape and the magnitude of the current can help identify the type of insulation material.
Different resins again?
Yeah, different resins like asphalt, polyester, various epoxies. They have characteristic DCR curve shapes. The guide shows typical examples for each, and they really emphasize the value of testing a new winding to get its unique signature, its baseline, so you have something to compare against later on.
Like taking a fingerprint of the machine's insulation when it's healthy.
Exactly like that. Then there's moisture. The guide shows how moisture dramatically changes the curve shape. It introduces strong nonlinearity, often looks like an increasing exponential shape, and it typically starts to show up above a certain voltage level.
So the curve bends upwards more sharply.
Right. They provide really powerful examples comparing, say, a heated, dry epoxy bar versus the same bar when it's wet, or a polyester winding tested under high humidity versus after it's been dried out. You see a clear difference moisture makes, and how drying can bring the curve back closer to a healthy shape. And the voltage where that nonlinearity starts can also be a key indicator.
How does aging show up on a DCR curve?
Comparing DCR curves from the same machine over time is really effective for tracking aging. General aging might show up as just an increased slope in the curve, which could indicate higher absorption current.
Okay.
But more localized issues, like delamination or internal defects, they tend to cause nonlinearity to start appearing at lower voltages than before.
So the bend starts sooner.
Right. The guide includes examples showing the difference between a new, nice linear epoxy winding and an aged one that shows both a higher slope and nonlinearity setting in. There's another really powerful example of an aged polyester winding that had known delamination.
What did its curve look like?
The DCR curve showed this sort of snaking pattern, followed by a sudden, sharp increase in current at a higher voltage right before a fault actually occurred during the test. And this correlated directly with the failure analysis later, which confirmed delamination was the cause.
Wow.
They also show how older asphalt insulation, which is prone to delamination, can show nonlinearity even at very low voltages.
And contamination, how does that look?
The guide gives an example of a modern epoxy winding that showed significant nonlinearity at various voltages and also a higher overall current amplitude compared to a healthy winding of the same type. And this behavior was linked back to visible contamination found on the winding surface when they inspected it.
Okay, so the DCR test isn't just about hitting a maximum voltage.
Yeah.
The shape, the slope, the linearity where it becomes nonlinear. It all tells a detailed story about the insulation type, moisture, aging, delamination, contamination.
It really does provide a rich signature. Okay, now let's move on to the second key test, the Polarization Depolarization Current test, PDC.
Right, this is the one with the two phases. Charging it up polarization and then discharging it depolarization.
That's the one. You apply a constant DC voltage for a set period. Could be 10 minutes, could be longer. And you measure the current during this polarization phase. Then you quickly remove the voltage source and short-circuit the test object to ground for a discharge period, measuring the current flowing out. That's the depolarization current.
And the big benefit of doing those two phases goes back to separating out the different current components, right?
Exactly. That polarization current you measure first, it includes the whole mix, the fast capacitive current, the slower absorption current, and any continuous conduction currents like leakage.
Okay.
But during the depolarization phase, when the applied voltage is 0, you're only measuring the capacitive current, again, very briefly, and then primarily the absorption current as the material relaxes.
So that's the key part. The depolarization current lets you isolate the absorption current, the part related to the material's internal state.
Precisely. You isolate it from those continuous conduction currents, which, as we said, are often heavily influenced by external factors like surface contamination or bulk moisture leakage.
So the depolarization current is particularly valuable for looking at the internal condition of the insulation itself, kind of free from that surface noise.
You got it. By analyzing the depolarization current, you gain insights into the intrinsic behavior of the insulation material itself, its health, its aging.
Okay. How do they usually show the data from a PDC test? Is it just numbers or graphs?
Graphs mostly. The guide shows a couple of common ways. You can plot linear current versus time, showing the actual polarity positive during polarization, negative during depolarization.
Okay.
But probably the most common format, especially with modern specialized test equipment, is plotting the logarithm of the current versus time. In these log plots, the depolarization time is usually reset to start at 0, and the current values are shown as positive magnitudes. It makes the decay easier to see.
Log plot. Got it. And you mentioned earlier the charging part can be used for IRP.
That's right. The polarization current over time is essentially what you use to calculate the insulation resistance profile, or IRP, which is our third test. We'll get to that.
Okay. And normalization. Still crucial for PDC data.
Oh, yeah. Absolutely crucial. Just like with DCR, normalizing the PDC curves by capacitance is necessary if you want to compare results from, say, an individual spare bar to a complete winding, or compare different phases or different machines. The guide shows a clear example of how normalization makes the curves from a spare bar and a full winding look comparable in shape, even though the raw currents were vastly different.
Okay. Now, beyond just looking at the curves, the guide talks about pulling out specific numbers from the PDC data to quantify things. What are some of those key parameters?
Yeah, you can derive several useful diagnostic values. From the polarization current, you can calculate the normalized polarization resistance, usually called RC-pol, at a specific time, typically 1 minute into the test. Right. Now, this value is influenced by pretty much everything. The insulation material itself, external conditions like humidity or contamination, the temperature, and the test voltage you used.
And the classic polarization index, PI, from the standard IE43 test, that comes from this polarization part too.
Yes, exactly. PI is just the ratio of that polarization resistance measured at 10 minutes to the resistance measured at 1 minute. It's derived from that charging current. The guide also introduces something called the polarization nonlinearity factor, or PNLF.
PNLF, what does that tell you?
That's the ratio of RC-pol measured at a lower voltage compared to RC-pol measured at a higher voltage. If that PNLF value is significantly greater than 1, it indicates that the conduction current is increasing non-linearly with voltage. That's often a sign of aging or developing defects.
Okay. What about parameters from the depolarization current? Since that part isolates the internal response, those numbers sound like they could be really powerful.
They really are. The normalized depolarization resistance, RC-pol, typically calculated at 1 minute from the start of the depolarization current. This one is independent of that direct conduction current.
That's the key difference.
Yes, so RC-depol is highly sensitive to the intrinsic state of the insulation, the material type, how well it's cured, its temperature, and also, to a lesser extent, the test voltage, especially as it ages. The guide really highlights RC-depol as being extremely useful for trending the internal aging of the insulation material itself, separate from surface effects.
So what does a low RC-depol mean?
An abnormally low RC-depol value, which means you measured a high absorption current during depolarization, suggests internal problems, things like incomplete curing, thermal aging damage, maybe mechanical damage like cracking, or moisture that's been absorbed deep within the ground wall itself.
Okay. And is there a nonlinearity factor for depolarization too?
Yeah.
Like the PNLF?
Yep. The depolarization nonlinearity factor, or DNLF, same idea. It's the ratio of RC dipole measured at a lower voltage to RC dipole measured at a higher voltage. If DNLF is greater than 1, it indicates nonlinear absorption current behavior, another strong indicator of aging or degradation happening within the bolt insulation material.
So these two, RC dipole and DNLF, they seem like the real stars of the PDC test for diagnosing the internal condition.
I'd say so. They're arguably the most powerful numbers you can pull from a PDC test because they effectively cut through that surface noise and tell you directly about the health inside the insulation material. Tracking these specific values over time gives you a direct line, essentially, to the material's intrinsic aging process.
That distinction is super helpful.
Yeah.
RC dipole and PNLF are influenced by everything, surface included, while RC dipole and DNLF focus on the internal state. Now, the guide mentions some influencing factors that are particularly relevant for PDC tests.
Yes, beyond the general factors like temperature, insulation type is still absolutely paramount. Those log current PDC plots look dramatically different for various resins. The guide shows distinct curves for asphalt, different kinds of polyesters, various epoxies. They even show variations within the same chemical families depending on age or thermal class. So knowing your material is step one.
Okay. What about the stress control coating? The guide says that can significantly affect PDC results. This sounds tricky.
It is tricky, and it's a really key point. It can be confusing if you're not aware of it. The stress control coating, especially designs that use materials like silicon, carbides, cassette tapes, can strongly influence both the shape and the magnitude of the PDC curves.
How so?
It can introduce distortion and nonlinearity, particularly noticeable at lower test voltages. But this isn't necessarily a sign of aging or a defect in the main ground wall insulation. It can just be the normal, expected behavior for that specific design.
So the coating itself affects the measurement.
Yes. The guide illustrates how sticky tape can cause a distinct hump or change in slope in the PDC curves, and it significantly affects derived values like RC dipole and PI. They explicitly state you need to understand this effect and factor it into your interpretation. It reflects a characteristic of the design, not necessarily a fault.
That's fascinating. Something designed to help manage stress actually complicates the test results if you don't know its signature. Does the voltage level itself influence PDC interpretation?
It can. For healthy insulation, the PDC values, like resistance, should generally scale linearly with the applied voltage. But the guide shows that with degradation, the PDC response can become nonlinear with voltage. Meaning the measured insulation resistance effectively decreases as you increase the test voltage. They show examples comparing the nice linear response of a healthy bar to the nonlinear response of an aged winding where the resistance drops off at higher test voltages.
Okay, so how do you put all this together to interpret PDC results for specific problems? Let's go back to moisture.
Right. Moisture absorption shows up differently depending on the insulation type. For modern epoxy, high humidity tends to increase the polarization current, but the depolarization current might be less affected, or it might even show signs of drying out over the test duration.
Interesting. What about older materials?
For older materials like asphalt or polyester, both the polarization and depolarization currents tend to increase significantly with moisture. And this effect is often more pronounced in aged insulation, especially if there's some delamination present. The guide also notes that the outage time before the test matters.
Why?
Because the insulation can dry out a bit or absorb more moisture from the air during that downtime before you test it. So consistency and outage time can be important for trending.
Okay. And tracking aging using those specific parameters, RC dipole and DNLF.
Yes, using those for trending is very powerful. A low RC dipole value combined with a DNLF greater than 1 is a strong indicator of internal insulation problems. Could be thermal aging, mechanical damage, delamination. The guide actually shows the PDC curves for the different phases of that delaminated polyester winding we mentioned earlier with the DCR test.
And the curves were different.
Yeah, the variations in the PDC curves between the phases clearly reflected the non-uniform degradation within that winding. It matched the DCR findings.
What about aging of the stress grading coating itself?
That can show up as changes in the overall shape of the PDC curves over time, particularly noticeable at the lower voltages where the coating's influence is strongest. The guide provides an example comparing PDC curves from a 35-year-old epoxy winding with C-beat grading to a spare bar of the same design. You could see how the shape of the curves, especially at lower voltages, had changed over those years due to the stress grading aging.
And incomplete curing, like in new insulation.
Similar to moisture, actually, lack of complete curing can result in an abnormally low RC dipole value. It means a higher than expected absorption current. The guide includes an example comparing the PDC response of a new winding, which they suspected was uncured, to that of a properly cured spare bar. The difference was clear.
Okay, that covers the PDC test. Really powerful for isolating that intrinsic material response using both polarization and depolarization. Now let's move to the third method, the insulation resistance profile, or IRP. This sounds like it's built on the classic IR test.
It is, essentially. The IRP is simply a graph plotting the insulation resistance IR value versus time. You derive it from DC IR tests performed at a constant voltage over a period.
Like the kind you do for a standard PI test.
Exactly. Or you can use the charging portion data from a PDC test or data from a step voltage test. You're just plotting resistance against time.
So you're just watching how the IR climbs over, say, 10 minutes.
Yes, but the key insight isn't just the final IR number you get at 10 minutes. It's the shape of that curve as it develops over time.
Shape again.
The shape is crucial. The shape of the IRP curve primarily reflects how the absorption current decays over time. That's what causes the slope of the IR curve to change as the test progresses. The overall level or height of the curve, that reflects the leakage resistance, both surface and volume conduction.
Okay. And the very beginning.
That very fast initial rise you see right at the start, that's dominated by the capacitive current charging up. But after that initial bit, the shape is mostly about absorption current decay. The continuous conduction current has a negligible effect on the shape itself, mostly just determines the final level it reaches.
So the shape is the main diagnostic tool here for IRP.
Precisely. The most valuable analysis comes from comparing the shape of the most recent IRP curve to historical IRPs from the same test object, looking for changes in that shape over time.
Does the voltage level or the duration of the IR test matter when you're generating an IRP?
Absolutely. While 10 minutes is standard for a PI test, you can use other durations for IRP. But the guide really stresses, that comparisons are only valid if you use the exact same test voltage, the same time intervals for recording data points, sampling time, and the same overall test duration every single time.
Consistency is king.
Totally. Ideally, the test should run long enough for the IR value to start leveling off, approaching a stable value, sometimes referred to as reaching 5 tau 5, which is about 5 times the insulation's time constant. It basically means the absorption current has mostly decayed away.
And like the other tests, history is absolutely vital for IRP analysis.
Critical. Trending IRPs from the same asset over time is by far the most effective way to use this technique. If you absolutely don't have historical data for a specific machine, well, comparing IRPs from different phases, or maybe against similar age machines, can provide some insights. But that consistent test setup every single time, non-negotiable for reliable trending.
Now, this part of the guide really emphasizes some practical points about the test circuit itself. What happens if you leave other stuff connected to the machine wiring when you do an IRP test, like cables or capacitors?
Ah, yes. This is a huge potential pitfall, a major source of misinterpretation. Other components connected to the machine wiring can significantly distort the IRP curve. Sometimes they make it look like the machine's insulation is a serious problem when the issue is actually with the connected cable or capacitor or something else entirely.
So isolating the machine is best.
The guide strongly recommends isolating these external components whenever possible to get a clean reading of the machine winding itself.
Okay, like the main power cables connecting the machine to the switchgear.
Yep. Long cables or older degraded cables, they can lower the overall IR values you measure. If you get readings that seem lower than expected, it's always good practice to disconnect the machine from the cables and retest just the winding itself. See if the cables were dragging the reading down. And for trending, you must be consistent. Either always test with cables connected or always test isolated.
What about surge capacitors? Those are often right there at the machine terminals.
Surge caps are a major influence on IRPs. They cause a very, very fast initial rise in the IR, followed by a really sharp knee, a sudden change in slope, and then the IR level will tend to plateau out at or near the resistance value of the capacitor's internal bleed resistor.
So it doesn't look like insulation behavior at all.
Not really. This behavior completely swamps the machine's true insulation response. Surge capacitors must be isolated before you perform a diagnostic IRP test on the winding itself.
Okay. And surge arresters. Similar issue.
Surge arresters can look dramatic on an IRP, almost like insulation breakdown. The curve might look perfectly normal up to a certain voltage, but then boom, the IR drops dramatically, maybe close to zero, as soon as your test voltage exceeds the arrestor's clamping voltage.
Well, they need isolating too.
Definitely. Isolate them before testing.
What about problems at the connection points, like dirty or damaged cable splices?
Those can show up as erratic results. You might see random spikes or fluctuations in the IRP curve. Now, these are often true indications of a problem, but the problem is with the splice contact, not necessarily the winding insulation. You'd likely need to isolate the machine from the cables to get a clean IRP that reflects only the winding insulation itself, and then address the splice separately.
Makes sense. And noise can then interfere, like electrical noise from the tester or nearby equipment.
The guide acknowledges noise is definitely a factor. Noise from the instrument's own internal power supply switching, sometimes called rail noise, can cause fluctuations or fuzziness in the IRP plot, especially when you're measuring very high resistance values. This could potentially mask the true absorption current decay shape or introduce spurious spikes that look like contamination. And external common mode noise, maybe from nearby variable frequency drives, VFDs, or other sources, can also cause spikes and variances. That could potentially be misdiagnosed as contamination. Good quality test instruments are designed to minimize this internal noise and often have features to alert the user if noise levels are high.
Field tests are more prone to this.
Generally, yes. Field tests, especially if you're not connecting right at the motor terminals, can be more susceptible to picking up common mode noise.
One last specific case. Machines with direct water cooling in the windings. Does the water matter for IRP?
Good question. The guide notes that for these types of machines, you need to be specific about whether the tests are done with the winding drained and dried out, or if cooling water is actually circulating through the winding ducts during the test.
And if water is circulating.
If you test with water circulating, the conductivity of that water needs to be consistent between tests. If the water conductivity changes significantly, your IRP results won't be comparable for trending purposes. So you need to control or at least record the water conductivity.
Okay, so managing the test circuit, the environment, the specific machine type, absolutely critical for getting meaningful IRP data that you can actually interpret and trend reliably.
Yeah.
Now, how do you interpret the shape and the level of that IRP curve once you have it?
Right, the interpretation. Again, the shape tells the story. Different types of insulation have characteristic IRP shapes. The guide contrasts, for example, the typical IRP of random wound machines, think smaller, mush wound motors.
What do they look like?
They're often flatter, show very high final IR values, tend to have a low polarization index, PI, often between 1 and 2, and exhibit a very sharp knee or change in slope early on.
Okay. Versus form wound, like in bigger machines.
Versus form wound machines, which use preformed coils. Their IRPs tend to be more linear, often rising more gradually with maybe a slighter bend over the 10 minutes. The guide also shows examples of characteristic IRP shapes derived from PDC data for various types of form wound insulation, polyester, asphalt, different epoxies. They all look a bit different.
And that high IR for random wound helps distinguish it.
Exactly. That very high final IR helps you distinguish a healthy random wound machine, which naturally has a low PI and sharp knee from, say, a form wound machine that has a similar low PI and sharp knee because it's suffering from moisture contamination.
Ah, okay. So how does moisture specifically show up on an IRP for, say, a form wound machine?
Moisture causes a very distinct left shift and a sharpening of that knee. Basically, the change in slope happens earlier in time and it's more abrupt. It also tends to decrease the overall slope of the IRP after the knee.
Why does it do that?
It's because moisture polarizes much, much faster than the solid insulation material itself, so that initial resistance rise completes quicker. Moisture often also shows up with erratic spikes, which can make it look similar to contamination effects sometimes, and it typically results in a low PI, often down around 1 to 2. The guide shows clear examples illustrating this left shift, the sharpening of the knee, and the flattening effect due to moisture. And again, the warning. Be careful not to confuse a moist form wound winding's low PI sharp knee shape with the normal shape of a healthy random wound machine, which might have similar numbers but for different reasons.
Got it. What about contamination on its own?
Contamination typically appears as erratic spikes or fluctuations riding on the IRP curve. You might see small spikes when the resistance is very high, but they become more severe, more erratic, and occur at lower IR values as the contamination gets worse. Contamination effects can also sometimes blend with moisture effects, making it tricky.
Are there examples?
Yes, the guide provides examples. One shows how cleaning a heavily contaminated rotor winding dramatically improved its IRP, fewer spikes, higher overall IR. Another shows an example of really severe spiking due to contamination. And a third example shows how contamination effects on the IRP changed over time as the machine also aged.
Okay. And aging, specifically thermal aging, how does that affect the IRP shape?
The guide states that thermal aging, which often makes the insulation brittle, tends to reduce the absorption current component over time.
Less absorption. So what does the curve do?
It results in the IRP curve appearing more linear. There's less change in slope over the test duration compared to a healthy winding of the same type. It just rises more steadily without that characteristic bend. They provide an example illustrating this effect of thermal aging making the IRP look straighter.
Interesting. Finally, uncured insulation. What does that look like on an IRP? You mentioned it was risky.
Right. Uncured varnish or resin, it tends to polarize faster than fully cured material. A bit like moisture does, actually.
So the shape is similar to moisture.
Yeah, it makes the IRP shape resemble that caused by moisture. It shifts to the left, shows a sharper knee. You might also see spikes similar to those caused by contamination, possibly due to conductive components in the uncured resin. So it can create an IRP that looks like a blend of moisture and contamination effects.
Tricky to diagnose then.
Can be. The guide shows examples comparing a new, suspected, uncured epoxy IRP to a properly cured one, highlighting the distinct shape change. And another example of what they called a weeping epoxy winding, basically resin still oozing out, tested before and after drying, with a note about the high humidity during the initial test.
Wow. Okay. So these three tests, DCR, PDC, and IRP, they really aren't just alternatives to the standard IR or PI tests, are they? They're giving you completely different kinds of diagnostic information.
That's exactly it. They're analyzing different aspects of the insulation's current response under DC voltage.
DCR looks at the current voltage curve under a ramp.
Right. Analyzing linearity, slope, where things change.
PDC uses both polarization and depolarization currents
to separate the internal material response absorption from surface leakage and conduction, using parameters like RC-depol and DNLF.
And IRP tracks the resistance versus time profile,
focusing on the shape of that curve, which reflects the absorption current decay, and comparing it over time.
So putting it all together, they move you from just a simple good-bad pass-fail status to a much more detailed picture of what's actually going on inside.
Exactly. By carefully analyzing these different signatures, while considering all those influencing factors we talked about, material type, temperature, moisture, contamination, test setup, and using normalization correctly, you can start to diagnose specific issues. Is it surface moisture? Is it absorbed moisture deep inside? Is it general thermal aging? Is it degradation of the stress grading? Is it surface contamination? Or maybe an incomplete cure from a recent repair?
And having that level of detailed understanding, that allows for much more informed maintenance decisions, right? Helping prevent those unexpected, really costly failures.
Absolutely. It truly shifts you from just reactive maintenance or purely time-based maintenance schedules towards true condition-based assessment, making decisions based on actual data about the insulation's health.
It's about getting that visibility into the insulation's condition, predicting potential issues before they become catastrophic, and ultimately improving the overall reliability of these critical machines.
That's the goal. Less downtime, more predictable operation.
So what does this all mean for you listening? If you're responsible for critical electric machinery, embracing these advanced DC diagnostic methods, like the ones outlined in this IE guide, offers potentially invaluable insights. But, and this is a big but.
Yeah, there's always a but.
As the document makes crystal clear, unlocking the full diagnostic power of these techniques requires discipline. It's not magic.
That really is the key takeaway. You need consistent testing procedures. You need to control for those environmental factors as much as possible, or at least document them. You need to carefully account for, or preferably isolate, other connected circuit components. And maybe most importantly,
History.
Building that history of test data over time for your specific machines, that is absolutely non-negotiable for effective trending and diagnosis. Without that history and that consistency in how you test, you're really missing out on the full diagnostic potential these methods offer.
So maybe a final thought for everyone listening to consider. For the most critical machines in your plant or your system, what's the very first step you could take, maybe even today or this week, to start establishing that vital history of advanced DC diagnostic test data? Where could you begin building that baseline?